Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are finally leaving stereochemistry behind, and we're going to begin looking at organic chemistry via the functional groups alkyl halides. In the alkyl halides section, we're going to examine both substitution and elimination reactions. Now, in order to study alkyl halides, we need to understand the basic divisions of the halide compounds. There are three types of organohalogen compounds. The type we're going to look at are called alkyl halides. They are alkyl groups that are bound to a halogen. We symbolize the alkyl group by an R group and the halide by X. Halide can be fluoride, chloride, bromide, or iodide. Alkyl halides are those in which the X group, the halide, is bonded to an sp cubed hybridized carbon. In opposition to alkyl halides, we have other types of halides, those that are called aryl halides, the symbol AR, air being an aromatic aryl group. Aromatic halides are those in which X is directly bonded to an aromatic ring. Bromobenzene, for example, would be an aryl halide. The third group of halide is vinylic halides. These are halides which are bonded to a carbon of a double bond that is sp squared hybridized. These carbon double bonds typically are not aromatic rings, and hence they are double bonded systems that are not in aromatic rings, and these halides are referred to as vinylic halides. Now, categorizing these halides can be somewhat challenging on some occasions, and therefore, using these three definitions, we can draw some molecules which we need to categorize either as alkyl, vinylic, or aryl halides. Now there are two other terms that can be applied to these. They are alkyl halides, and there are special types of alkyl halides. The first is the benzylic halide. The benzylic halide is a halide that is bound to a benzyl group. In other words, X is bound to an sp cubed carbon which is attached to an aromatic ring. This is referred to as a benzylic halide. Now let me reiterate, benzylic halides are alkyl halides. Benzylic halides are alkyl halides. Likewise, if the halide is bound to an sp cubed carbon, so if X is bound to an sp cubed carbon, which itself is attached to a sp squared carbon of a double bond, then this is referred to as an allylic halide. Now both allylic and benzylic halides are examples of alkyl halides. There's some classifications, if you like, special cases of the alkyl halide groups that we're going to be studying. Now, utilizing the terminologies benzylic halide, allylic halide, vinylic halide, and aryl halide, you can use these definitions to categorize molecules in those four categories. For example, I could draw several structures here, and if I do so, so here are some polygon line formulas of molecules. Why don't you categorize these as allylic, benzylic, alkyl, aryl, or vinylic halides and see what you can come up with. Now, in terms of physical properties, alkyl halides consist of carbon with a halogen bond, either fluorine, chlorine, bromine, and three other carbons, or three other groups. They could be carbons or hydrogen or other halides. And molecules such as these have a physical property that arises due to a polar covalent bond. The halogen is more electronegative than carbon, so it gets a delta minus. The carbon gets a delta plus. This leads to a dipole moment in the carbon-halogen bond. Molecules such as CH3Cl, for example, would possess such a bond. Molecules such as CHCl3, chloroform, would also possess three such bonds. These molecules would possess a dipole moment. Molecules such as CCl4 and CBr4, carbon tetrachloride and carbon tetrabromide, possess polar bonds, but the dipoles are opposed to each other and point in opposite directions. And hence, although they have polar bonds, they are nonpolar molecules. Because the dipole moments cancel. Now, in terms of physical properties, organohalides, alkyl halides, are typically denser than water. They typically are insoluble in water. They tend to be soluble in most organic solvents. They do not react with concentrated acids, so typically they're inert with respect to concentrated H2SO4. And they can dissolve or are soluble in mixtures of water alcohol. So if you do need to dissolve them in an aqueous mixture, you can dissolve them in the presence of water and alcohol. Okay. In terms of nomenclature, most of the nomenclature of alkyl halides has already been dealt with. I'm not going to rehash that. I'll give one example. But in the nomenclature of alkyl halides, IUPAC names typically are named as alkanes with halogen substituents. Chlorides are given the prefix chloro. Fluorines given the prefix fluoro, bromine, bromo, and iodine, iodo. And so we have here chloromethane. With regards to common nomenclature, we have methyl chloride. Now, very important is the kind of halogen we're dealing with as well. This type of halogen is referred to as a methyl halide. Methyl halides are the halogen is attached to a methyl group. We also can have primary alkyl halides. A primary alkyl halide has the halide bound to a carbon, which is bound to a single carbon, such as, for example, ethyl chloride or ethyl bromide. We actually look at the carbon that bears the halogen, and we ask the question, how many carbons are attached to it? So in this case, we've already discussed this previously, but in this case, carbon that has a halogen has one carbon to it, so it's primary. A secondary halide would have two carbons attached to it, that is attached to the carbon that bears the halide. Tertiary halides would have a carbon that bears 3. And often we also use the term allylic or benzylic halide to describe the kind of halide. In this case, the carbon with the X group has 3 carbons attached to it, so it's tertiary. Now, Having laid the groundwork, having discussed the types of halides that are there, their physical properties, their nomenclature, we want to now consider some of the basic reaction paths that alkyl halides can follow when reacting with other compounds. The first one we're going to look at is the substitution reaction. Now this represents one of the more common and important reaction pathways in organic chemistry. It is a reaction in which one atom, ion, or group replaces another in a molecule or ion. So it's substitution because one group is coming in and replacing another. This can be readily exemplified by the reaction of a methyl halide. So here's the lone pairs on my halide, and I'm going to attack it with a group that I'm going to give the symbol Nu to, and I'm going to give this Nu group a lone pair and give it a minus charge. Now we've already indicated that the carbon bond to the halogen is polarized. There is a delta plus on carbon and a delta minus on the halide. This means the negative charge on the group labeled Nu is attracted to the carbon, thusly. But carbon already has 4 bonds. Carbon has a full complement of 8 electrons of filled octet. In order for these electrons to form any kind of bond to carbon, a bond must break. In this case, the X group grabs both electrons. We end up forming a new bond to our Nu group. And the halogen has left and now has all the lone pairs around it and a negative charge. So a negative charge is transferred to the departing halogen. Now, this Nu group is called the nucleophile. Nucleophile is a term we use meaning nucleus seeker or nucleus lover. It is a name of any group that would seek out a delta plus. Nucleuses, or the nuclei are positively charged. Because nuclei bear positive charge, whatever seeks them out is referred to as a nucleophile. These are typically negatively charged groups or groups with lone pairs. The organohalide is called the organic substrate. It is that group which is being reacted upon. The X group on the organic substrate is referred to as the leaving group. The leaving group is that halide in alkyl halide substitution reactions which actually departs the molecule. And since we now have the nucleophile attached to the methyl group and the X having departed, we have carried out a substitution for the substituent on carbon. Because of the delta plus on carbon, it's susceptible to attack by good or strong nucleophiles. One should note that halide ions are typically very good leaving groups. The reason they're good leaving groups is they're easily displaced, and this is because they are weak bases. Typically, weak bases make good leaving groups. Now, fluoride is an exception to this. The F- is a poor leaving group because it's a fairly strong base. But all of the other halogens tend to be very good leaving groups because they're weak bases. In terms of relative reactivity, the reaction rate can be directly related to leaving group ability. If I use the same nucleophile and I compare an alkyl iodide to an alkyl bromide, I find the alkyl iodide reacts faster than the alkyl bromide. The bromide reacts faster than chloride. And the chloride, of course, reacts faster than the fluoride, which, because it's such a poor leaving group, probably doesn't react at all. The reason for this trend in reactivity is directly related to base strength. As we go down the group, because size increases from fluorine to chlorine to bromine, HF is a weaker acid than HCl. HCl is a weaker acid than HBr. HI is the strongest acid. Because the atom is so large and H is so small, you have poor orbital overlap, and the H plus leaves HI more rapidly. If HI is a stronger acid, I minus is the weaker base. Weaker bases are therefore better leaving groups. So I minus is the better leaving group because it is the weaker base. Okay. What about the nucleophile here? Well, if we focus on the nucleophile, a nucleophile is any atom, molecule, or ion that can act as an electron pair donor. It's a Lewis base. You've already memorized your Lewis bases. Lewis bases, remember, require a lone pair of electrons. In order to act as a Lewis base, you must have a lone pair of electrons you can donate. So a nucleophile is also a Lewis base. A nucleophile must have a lone pair of electrons. It may or may not have a negative charge, but very often it does. Every one of these molecules I am drawing has lone pairs, though not all have negative charges. Okay, so they all bear lone pairs. Some of them are negatively charged and some are not. So, the attacking species in the substitution reaction is referred to as the nucleophile. It attacks the organic substrate, and the group that departs is referred to as a leaving group. When the attacking group is a nucleophile and substitution for another group occurs, the reaction is referred to as nucleophilic substitution. So we often call this substitution reaction nucleophilic substitution. And so I would put this word out front. A nucleophilic, this would go out here. Nucleophilic substitution reaction. The other point to note is that I'm using full-headed arrows to move electrons. Both electrons, since 2 electrons are donated by the nucleophile, both electrons of the bond go, the carbon-halogen bond, go towards the halogen to create this lone pair. This is called heterolytic cleavage. Heterolysis, or heterolytic cleavage, is the breakage of a bond where both electrons go to one group. Back when we were looking at bond dissociation energies, we compared heterolytic bond cleavage to homolytic cleavage. When determining bond dissociation energies, we learned that we had to use homolytic cleavage. What we see here in this reaction is heterolytic cleavage. Both electrons of the bond go towards the halogen. Okay. Well, we can list 3 essential factors that control this type of substitution reaction. 3 issues we must be extremely concerned with that will obviously influence the reaction. And essentially, we've listed them already. And that is the nature or structure of the alkyl group. The second thing, of course, is the nature or structure of the leaving group. And the third is the nature or structure of the nucleophile. Now, when I say structure here, I'm not so concerned with the actual atoms, but the structure of the nucleophile affects its property. The structure of the alkyl group affects its properties. We're really interested in the behavior or properties of the molecule based on structure and how they influence this type of interaction. We have seen the nucleophile, the organic substrate, and the leaving group. Well, it's not surprising that all 3 influence the extent to which such nucleophilic substitution reactivity will take place. Now, it would be nice if this was all that could occur, but often in organic chemical reactions, you get different reaction types competing with each other. And one reaction type that competes with the substitution reaction is the elimination reaction. This is a reaction in which a stable species is eliminated from the molecule. And it's always followed with the formation of a multiple bond, either a single or double bond. In the case of halogens, the reaction is often called dehydrohalogenation, because the reaction is always followed by the loss of a hydrogen and a halogen. Now, instead of having a nucleophile attack, in this reaction we will have a base molecule attack. I'm going to call this base, and we can make it negative. Now, you begin to notice the difference when you look at this reaction between the term base and the term nucleophile. Nucleophiles attacked carbon. They were attracted to the delta plus of carbon. But as we know, bases attack protons. So this reaction is driven by the base attack of a hydrogen that is attached to a carbon atom. The base attacks the hydrogen, grabs a proton. 2 electrons from the carbon-hydrogen bond move towards the other carbon to build the pi bond. And the 2 electrons from the bromine bond move out to bromine. You end up with the BH molecule plus a bromide anion, and lastly, we end up with our multiply bonded molecule, which is now an alkene. Elimination reactions, when carried out on alkenes that have halogens on them, can yield alkynes. Typical bases, of course, are hydroxide. If hydroxide was used as our base, the BH unit would have been an H2O molecule. So if hydroxide was the base, then the product BH would have been H2O. So the base acts as an electron pair donor grabs the proton. We get heterolytic cleavage again from the bromine carbon, and a pi bond is formed. So the elimination reaction, sometimes called dehydrohalogenation, is a reaction that occurs in direct competition with substitution. We can summarize this competition by taking a look at the molecule 1-bromopropane. I can react 1-bromopropane with the molecule hydroxide. If it undergoes nucleophilic substitution, the OH group substitutes for the bromo, and I get CH3, CH2, CH2OH, plus Br minus. I get 1-propanol. Hydroxide acts as a nucleophile because it attacks carbon. But in competition with this reaction, hydroxide can attack a hydrogen on the carbon next door to the carbon that has a bromine. If I use Greek letters to label my carbons, the bromine-bearing carbon, or the carbon that bears the bromine, called alpha. The next carbon could be beta. The next carbon would be gamma. The hydroxide attacks a hydrogen on the beta carbon. Because of this, the elimination is called often beta dehydrohalogenation. The hydroxide pulls off a proton, becoming H2O. You get a pi bond forming and the bromine leaves. OH minus is acting as a base in this reaction. Again, you get Br minus, and the proton added to the hydroxide gives you a molecule of H2O. Now, which reaction actually occurs depends on several factors. We have to be interested again in the structure of the alkyl halide. We're going to find out that whether that alkyl halide is primary, secondary, tertiary, methyl. Let's put Me for methyl. Primary, secondary, or tertiary strongly influences the nature or the extent to which either substitution or elimination occurs. Also important is the nature of the attacking group, be it nucleophile or base. The nature of the attacking group. For example, is hydroxide a strong base? If it's a strong base, that may favor base attack. Is hydroxide a strong nucleophile? If it's a strong nucleophile, that could favor nucleophilic substitution. The extent to which the attacking group is either more nucleophilic or more basic will influence the degree to which you get either elimination or substitution. Another factor that can influence such reactions that we haven't mentioned yet is the nature of the solvent. The exact nature of the solvent can have a direct influence on this type of reaction. And the last key point, of course, that seems to bear a lot in all reactions is reaction temperature. Different reactions are favored at different temperatures. And so we're going to find that certain conditions, reaction conditions involving temperature, will favor substitution over elimination or elimination over substitution. Now, typically, we find, and we have to be able to rationalize this, methyl and primary alkyl halides seem to prefer, more often than not, and this is just a general rule, substitution reactions. The tertiaries, and there are exceptions to this, tend to favor the elimination reaction, but you can get them to undergo substitution. The secondary alkyl halides tend to go either, depending on the reaction conditions, temperature, solvent, and other conditions, the nature of the attacking group. So they tend to go either, and you have to look very closely at the conditions. Now, before we actually proceed and examine in detail both substitution and elimination reactions, we need to have a better or more in-depth understanding of what factors favor nucleophilicity. We've already established some trends based on periodic tables for acidity, which can be used to help establish a basicity trend. But we need to do the same thing for nucleophilicity, nucleophile strength. Do all the factors that cause some molecule to be a powerful base also make it a powerful nucleophile? Well, we're going to take a look at that in the next Scribblecast lecture. My name is Dr. Brian Lloyd. This is my Scribblecast,